Perfect.
All right, so I will introduce you. So hey everyone, thanks for coming. Today we have a talk by Kelian Häring from Amsterdam University, who is going to talk to us about from data to the analytic S matrix, a bootstrap fit of the pion scattering amplitude. Thank you very much for accepting our invitation, and please go ahead.
Hi everyone. Well, first of all, thank you for the invitation and the interest you have in this work. So this talk will be based on the paper that appeared 2-3 weeks ago with Andrea and Ning Su. And as I understood, the audience is quite large, so I will start with a general introduction of the bootstrap and the S-matrix bootstrap, and then go more into the detail of this study. So please interrupt me anytime you have any question. I think it's better this way. So to start, okay, what are the tools that we can use to study quantum field theories? So we have, I guess, many at our disposal. The first of all is what we learn at school is perturbation theory, computing Feynman diagrams, loops, 1, 2, 3 loops. And then we can use lattice, integrability, or different perturbative or non-perturbative technique, each of them in different regimes. And then finally, we have the bootstrap. So this list is not non-exhaustive, but it's a list of possible tools to study quantum theories. And finally, we have the bootstrap. In the bootstrap, we must generally study what is possible in the space of quantum field theories. So we'll not, in general, choose one specific quantum field theory, but look at the space of quantum field theory. And how do we do that? So we study observables, and particularly we study the S matrix because we will be interested in the quantum field theories with a mass gap and that appear in the real world. And so what is the S matrix in a bit more detail? So here we will look at the 2-to-2 scattering amplitude. So we have particles A and B going to C and D, and this is denoted as the S channel. And so the scattering amplitude is a function of two variables, S, the total center of mass energy, and T, which is the momentum transfer, or equivalently, the scattering angle. And there is these three famous Mandelstam variables, S, T, and U, and they're related S plus T plus U equal to 4 times the mass of the particles. And so here I will focus on the case when you have a gap and we have a massive external particles, and also will be in D equal 4. And so this amplitude is not has some constraint, and I like to call them the bootstrap constraints. So the first of which is anisotropy, and is a consequence of causality. And it's simply that the statement, so this function T is a function of two variables, S and T. And so anisotropy is a statement that if you fix T, for example, and you look in the complex S plane, so this function is analytic in the full S complex plane, except from cut coming from causality. So we have the S cut here, and you see it's not at form square, which is the threshold to have some physical scattering process. And so if you want to get the usual amplitude that you can measure, you need to approach its curve from above. It's a usual Feynman-Einstein prescription. And then because we fix D and the three Mandelstam are related, you can approach the U channel going from below this cut here. So this is the first properties of the amplitude. It's the anisotropy properties, and is the first letter A here in red. The second constraint is crossing. It's simply a statement that I can look at the scattering process from different perspectives. I can look from the left to right or from top to bottom. And so I can, this is the respective the S and the T channel. And it's simply the statement that if I scatter particle A and B going to CD, or particle A antiparticle C going to antiparticle B D, it's given by the same analytic function by permutation. And similarly in the U channel. And finally, the third constraint is unitarity. And for that, unitarity is simply the conservation of probability. And for that, it's convenient to go in the partialist basis. So you can think of that by the fact that T is a function of two variables, S and T. And so you can trade the second variable T for the fixed angular momentum. And why is it interesting is because when you do a scattering process, the angular momentum is conserved. And so in this basis, unitarity is diagonalized because probability is conserved at fixed angular momentum. So you can do this decomposition here, and it's just some numerical factor. This is the Legendre polynomial, which depends on the scattering angle. X is cos theta, the scattering angle. And these Fj are the dynamical information. They are the partial wave amplitudes. And so to express the unitarity, it's convenient to build this combination of the scattering angle, the partial wave amplitude with some kinematics. And in its notation, unitarity is simply a statement that this Sj is bounded by 1. Absolute value of this Sj is bounded by 1. In terms of Aj, it's simply a statement that the imaginary part of Aj are positive, but not only positive, they're also bigger than the absolute value square of the absolute value square. Okay, so that's the 3 basic bootstrap constraints. And now what I would like to do is give a simple example of how to combine these different ingredients in order to get some non-trivial results on quantum field theories. And so for that, I will consider maybe one of the simplest scattering amplitude, a massive scalar with Z2 symmetry. So it's like lambda 5 to the 4. And so if you expand this energy at what is called this crossing symmetric point, so if you do subtract from the Mandelson variable this 4/3 of m², you inside this real strip here, this Mandelson triangle is the amplitude is real there. And so it has a finite radius of convergence. So if you expand the amplitude there, you have a first term, which is constant. Then you don't have S plus T plus U because it's just equal to 4m², so that's not there. Then you have a second term, which is just this combination. And roughly speaking, this is given by lambda 5 to the 4. And this is like a d5 to the 4 term if you do perturbation here. And so these are what we call low energy observables, because they are defined inside the crossing symmetric points. And you may ask, can they take any value? And so in order to go forward, we will need an extra ingredient, which is the Martin-Froissart-Bound. It's about the UV behavior of this amplitude. It's simply a statement that the amplitude is bounded if you go to the complex plane by S². So it decays faster than S². So this is not ad hoc. It's actually can be derived simply using the same constraint, but I will not do that too. Okay, so what can we do now to extract constraint on this coefficient? So to start, we'll write the Cauchy integral. So here, I'll write the Cauchy integral with not just on the amplitude t, but amplitude divided by this kernel, which simply decay faster than S² at infinity because it will be allow me to drop an arc. And so this is simply a true equality. And this contour here is simply around this point S. So now I can use the first constraint, which is analyticity. So I can deform this contour in the complex plane at fixed d, and it will encapsulate this branch cut, the S cut and the U cut. And now I can collapse, and then it gives me the discontinuity or the imaginary part of the amplitude times the kernel. So I have one for the S cut here and one for the U cut that I label here. And Ks is some kernel that we can simply get by looking at the first example. Then you have need to pick up the poles here that are coming from this kernel, and simply give you something linear in S times the function. Okay, so here we use analyticity because we deform the contour. The next step, we can use crossing. So using crossing, we can bring this left cut to the right side. And so we have now a single integral from 4m² to infinity of the imaginary part of the amplitude times, again, a kernel. And finally, so now we have a integral representation of the amplitude in terms of its imaginary part times the kernel. And now if I expand both sides at small s and t at the crossing symmetric point, I can straightforwardly get that G2 this coefficient G2 that we have in front of this S bar square plus T bar square plus Q bar square is given by this integral. Now this integral, this kernel, simply becomes this S prime minus 4/3 of n squared to the Q. And this part is explicitly positive in the region of iteration. And thanks to entirety, this imaginary part is also positive. And so here, using A, C, and U, so these three constraints, we directly get that G2 is positive. So I think it's a simple way to see that using these three constraints, we get some bounds on the low energy observable. But now, of course, here I use only positive. Yes.
I have a question. Could you go back? Yes. So when you express T as that integral, why is it specifically that kernel?
Yeah, I choose this kernel because it's a crossing symmetric in S and U. And so it simplifies my life because then the kernel here, it's also simpler. But you can choose any subtraction point. And then depending what you choose, you will have a different function f basically here. But it's not so important.
So that's just a convenient kernel that you use.
Yeah.
You could have used any other.
You can choose different kernel, but it's convenient to choose a kernel which is SU symmetric.
Right. Okay.
Because when you bring the left cut to the right cut, then it will be simpler.
Yeah. Okay. Thanks.
Yeah. But you have a different choice in literature, and depending on the choice you have, you can do different things. Yeah. Thank you for the question.
Okay. Thanks.
Yeah. It's also given a really nice expression for G2. That's one of the reasons I chose this one here, but because I wanted to have this factor here. But, yeah. Okay. Really good. Yeah, so far in here, I only use the fact that the imaginary part is positive, but we know that entirety is more than that. It's not only that imaginary part is positive, but it has to be bigger than its absolute value squared. And so far, in a sense, what we use, if you look at this graph here, is only the fact that the imaginary part must be in the lower half plane. But entirety is much more constraining. It's a statement that the partial wave amplitude, F, has to be inside inside this green disk. So if you do that, and you get much more constraint on the Wilson coefficient from the observables. And for example, this was obtained, the boundary is obtained from two paper in 22 and 23, and give you a bound on G2. So not only a lower bound on G2, because before we only get that G2 is positive, now it's also a bounded from above by this tip here. And also G0, the constant term, is bounded from two sides. So it's not sign definite, but it's bounded in both sides. Okay? So how can you get such constraint? Because now you need to implement nonlinear constraint. So for that, there is a multiple approach in literature. And the one I would like to follow here is what is called the primal approach. So instead of using dispersion relation, as we did before, we'll explicitly build an amplitude. So how can we do that? So we will build an amplitude which has the correct analytic properties. So for that, the amplitude we saw that was analytic in the S complex plane, except for cut starting coded from causality, starting at prime squared. And so we do a map from the cut plane to the unit disk when this absolute prescription is mapped to this upper half unit disk. And this map is simply this row map that is now quite standard in the, I guess, in literature. And doing post-crossing, we simply do an expansion of these rho S, rho T, and rho U variables that we then project in the constraint on NC and U, and we symmetrize this coefficient in front. And so now we have an amplitude which is explicitly analytic and crossing symmetric. And what is left to do is to impose entirety. How do we do that? Well, we can decompose this amplitude into partial wave. And now this nonlinear relation can be recast in a matrix semi-definite constraint using this combination. And now this metric is linear in the partial wave. And so we can use some numerical solvers such as LDPB in order to find some bounds. And the group of people I mentioned before, they did that on this explicit amplitude, and they get this what is called the leaf amplitude, the leaf in the Bootstrap. So at this point, I would like to emphasize that because we built an explicit amplitude, we first of all got bound, but we did not only get bound, we have an explicit amplitude which satisfies both identicity, crossing, and unitarity. And so now we have such amplitude, we can look into it and inspect some features. So we can look at resonances. And for example, in this work we did last year with Dennis, Andrea, and Francesca, this was for massless particles. So we extracted resonance, and then we did an analytic continuation in speed and extracted the full rigid trajectories. So here you see the leading and subleading trajectories in red, orange, and blue. So here, I will not go in detail into this, but just to emphasize that you have the outcome of this is not just bound, it's a full amplitude. And this is what we will use in this project, or in the remaining of this talk, is the fact that we don't only have bounds, but we have a full analytic amplitude. Okay, so other question on this part? Otherwise, I will move to maybe the core of this work.
So yeah, can you go to the graph of the last slide?
Here?
Okay. So in your answer, I guess you have to assume some bound for the sum in ABC.
Yeah, we truncate, exactly, yes.
Yeah, right. So how does that plot change when you?
Which plot?
The
this
last
one?
No, the last one.
This one?
Yeah.
See, this one.
Yeah.
Is the shade of blue and of orange here. So here you see it's how when we increase this. So we do a sum. We can look at some n max. There's the max power of which the sum of the three, and when we increase, we go to the left here. Yeah.
Okay. So the ones. Okay, I cannot see. Yeah, what are the liberals of the axis?
So here, sorry, yes, a bit more. Here's the real part of the resonance, and here's the spin.
Oh, okay.
So you see, here we go to complex spin, so we go to fraction value of a spin to follow the trajectory, because here we have resonance and we want to see that they were connected in spin, and so we continue in spin. We did fraction value of spin to actually, yeah.
Okay. Thanks.
Yeah. So at fixed spin, we extracted the mass by looking at the zero in the complex plane, and we plotted that here. Any other questions? Okay. Let me go to maybe the meat of today. So today, as maybe the title was mentioning, the goal, I would like first to emphasize that the goal is not to get bounds on these observables, these Wilson coefficient observables, but is to fit data. So here we will really use the power that we get an analytic function out of the Bootstrap problem. And so first thing I will do is quickly go through a review of pi scattering to get up to speed. And then I will detail the fit strategy that we follow in this work, and in order to fit the data. And then I will present the result that we obtained. So what are the pions? So the pions, they're simply the pseudo-constant boson of the original chiral symmetry of the QCD Lagrangian. And this work will neglect the isospin Briggs effect. So all the pions will have the same mass that will set to 1, and this will fix the unit. We have to choose the unit, and we choose the unit for the pion mass 1. So the pions are the largest particle in the crystal spectrum. And so what does it mean? It means that they transform in the vector of O3. And so if I scatter pi A, pi B to pi C, pi D, the scattering amplitude now has a label of the which vector representation it's in, and it's given by this combination. And you can see that any of such amplitude is given by a single analytic function, this A, that is symmetric into T. And so only one analytic function parameterizes the full scattering amplitude of pion scatter. So because we consider that isospin is conserved, so in the scattering process, if isospin conserved, it's convenient to go into the isospin components. So here it's simply what are the isospin amplitude in terms of this A amplitude. So we have the isospin 0 channel, the unsymmetric channel, and the symmetric channel. And as before, now we can decompose into partial wave. And because both isospin and the spin is conserved, unitarity is best explained in this basis. And so the partial wave is simply obtained by convoluting the amplitude with the partial wave, with the Legendre polynomial. And here I use also this slide to define what is the phase shift. So if I build this combination S, which is 1 plus I T roughly, then I can the absolute value plus a phase, and the phase here is what is called the phase shift. And so because of this definition here, the phase shift will always be real. Okay. So now I have a pi scattering, so I have different resonances. So what is known about the literature, in the literature or in the PDG about this spectrum? So if you open the PDG and you look at the meson spectrum and what happened in pi scattering, so you see different particles. So here everything is in unit of m pi equal to 1. So the pion would be here. And so here you have different particles. So you have the sigma. So in this plot, the spreading in the vertical direction is inserted on the mass. And the width of the box is actually the width of the particle. See, the sigma is known to have a large width and a low mass. So it's the first one that you see. And then in the same channel, you have the F0, first F0 and second F0 at roughly 980 MeV and etc. Then you have the rho, which is really sharp. It has a small width and is the dimension really precise. And for example, you also have the rho 3, which is on the same trajectory of the rho particle, but it has a spin. So there is also more, but okay, some of them are less sure. And here we plot the one on the low end.
So sorry, can you say again, what is the width, the horizontal width of the box mean?
It's actually the width of the particle.
Okay.
The decay width, yeah. We didn't plot the unit, but it's roughly represent the decay width of the particle. Yeah.
Okay.
And okay. Here we label that by family, by isospin and spin of the particle. Yeah.
Right.
Yeah.
Okay. Yeah. Thanks.
Okay. Yeah. It's yeah. We don't plot the error on the width of the particle. It will be a third dimension. We don't have. Okay. So now I would like to give some detail on the fitting strategy. So the first thing to do is to construct an ansatz. And so as you may guess, it will be based on the primal ansatz that we discussed before. And then we would like to do a fit. And so we need to choose a set of fitting parameters because there's infinitely many choices, and we need to choose carefully the set. And then because we want to fit data, experimental data, we need to optimize these fitting parameters with experimental data. So I will now describe each of these steps here in some detail. So the first thing we want to do it's to construct analytic function. So we need to construct analytic function that is crossing symmetric. And is this A ansatz is symmetric in T and U. And so now, as before, we make an expansion in this row variable. But now, because it's only symmetric in TU, here I give you the explicit construction that we use. And we have a row S times row T plus row U and row T row U symmetrization. And so the parameters of the ansatz, the free parameter, they are the alpha and this beta. And then here you see that we sum of a sigma. And so these row variables, it's a map from the complex place to the unit disk, and it has a center. And the chosen in center tells you basically which region in S do you best represent. And so because the pion scattering amplitude is a multi-scale amplitude, it has chiral physics at S close to 1, but then it also has a lambda QCD, so it has a rho, it has many things around S equal to 50 in this unit. And so we find it convenient to make this multi-foliation ansatz, which is tailored for this problem, which has a different center of the row mass. So, okay, it's a bit technical, but we find it convenient to have a better convergence of amplitude. And so this, as you saw before, we need to truncate in this number of parameters we have. So we have this parameter n here. And so the number of free parameters is given by this n for each choice of this sigma. And in practice, we have order 500 free parameters. So now this ansatz is explicitly crossing symmetric and satisfy anisotropy. So the remaining constraint on these parameters is unitarity. Okay. And so unitarity would be also imposed using SDPB as before, as a nonlinear constraint. Okay. And now we need to choose the fitting parameter. In principle, there is infinitely many observable. So if I compare to what we had before in this expansion in the crossing symmetric point, so we had the G0, we had the G2, but this list continues and I have infinitely many in principle. And so we need to choose carefully which one to pick in our procedure, because we want to compare experimental data, but we cannot tune infinitely many in order to fit the data. It's impossible to do with a finite computer. And so in this work, we choose 3 types of fitting parameters. The first one are the chiral zeros. So if you do chiral perturbation theory, you realize that the partial wave amplitude, they are 0 in the real strip, so below threshold. The partial amplitude in the isospin 0 spin 0 channel, and isospin 2 spin 0 channel, they are 0 in the real strip. And this is a consequence of if the pion were massless, a simpler statement that they will be soft and in the soft limit. They will be 0 in the soft limit. Then we'll assume the presence of some particle in the spectrum. So because we want to fit data, we want to fit data that have some spectrum, and it's only convenient to assume the presence of some particle in the spectrum, but will not impose a position. The position will be decided by the position is a fit parameter and will be decided by the algorithm in order to better fit the data. And so when we have a particle in the spectrum, so it's translated in a 0 in the complex plane in the corresponding channel, and so the position of this 0 will be a parameter of alpha. And the last one is the scattering length. So this is really the analog of this G0, G2 that we had in the beginning. And if you expand the real part of the partial amplitude at threshold, so you have the first term is the scattering length. It's maybe known to you from quantum mechanics. And we'll show this triplet, which is the first 3. So in the lowest spin in each isospin. And so now I haven't told you what we will maximize in our procedure. So for that, we will look into these scattering lengths. And we take inspiration from a work from 2019 by Andrea, Joao, and Pedro. And in this work, it was the revival, basically, of this pion bootstrap using non-motivity methods, and I realized the following. If you fix one of the scattering lengths and two chiral zero, these two chiral zero to these values, which are close to experimental ones, you have a kink in the R region of the two remaining scattering lengths. So this kink is here. So this kink was really interesting because, first of all, if you compare with experimental prediction of these two scattering lengths, so it's given by this red box, so it's really close to it. So it is hoped that the amplitude you get at this kink is close to being a good candidate for the scattering amplitude. But not only that, if you look inside this amplitude, and they did that in this work, you observe that this amplitude here already have a rho and have a sigma. So they don't have the correct mass, but they have a hint of the correct spectrum. And so in this work, we follow this scene. And so what we will do, we will trade off these three parameters. So we'll fix one of them, and we'll maximize the two remaining one along this one-dimensional line and close to the kink. And this will be the target of our numerics. And so at the end of the day, the fit ansatz is the following. So you choose a set of chiral zero, one scattering length, and this angle in which you maximize. You fix some values of resonances. Then you maximize in this ansatz this objective, which is a normal objective. So it will likely go to this kink. With this constraint fix, so it's simply using this choice here, so imposing new target. So at the end of this procedure, what you get an amplitude which depend on this choice of parameters. So all in all, we have a set of fitting parameters, this theta. You give me a set of parameters. So in total, there are 12 of them because the mass are complex, both the mass and the width of the particle. The width is basically the imaginary part of the mass. You give me a set of theta. It spills out an amplitude. Okay. So now we have an explicit construction of an amplitude. And what we want to do is to navigate in this space of theta of parameters in order to fit the experimental data. So how do we do that? So we construct an amplitude using a set of theta. We compute the chi-square. So the chi-square is simply you compute the partial wave of your amplitude and you obtain the phase shift. And then you compare with the experimental one that you can find literature. And this is a function which at its minimum is the best one that will describe all experimental data. So the goal is to minimize this chi-square in order to have an amplitude which characterizes best the experimental data. And so this chi-square function is in principle really non-convex. It's a complicated function. It's a function of 12 different parameters. And in this work, we used an algorithm to navigate in this space of parameters and search for the minimum, which is called the particle swarm optimization algorithm. I will not go through it in detail, but it's a nice optimization procedure, which is basically gradient free. And the main idea is to just navigate in the space of 12 parameters and look for minimum. Okay, so I think I'm ready to go now to the results. So let me know if you have any question up to now. Okay, very good. So first of all, what are results on the phase shift? So I haven't yet told you what a phase shift we fit with. So the data we take are these orange error bars that are experimental measurements. in a different channel. So in the S0 channel, S2 channel, in the D0 partial wave. So it's either spin 0, spin 2 partial wave, and in the P wave. So the orange error bar are the experimental measurement, and the green one, they're coming from lattice. So there is a few lattice data that we also use. In particular, here, this green point was really important for us to stabilize the numerics. And what you see in blue, so the dark blue is our best amplitude, our best candidate is the one with the minimum chi-square. And all the light blue that you see in these different plots, they have chi-square which is reasonably close to the minimum. And we plotted together it's an estimate basically on the error band of the fitting procedure. Okay, so the first thing you see is that the amplitude constructed really passed through all the data that we have, at least up to some up to the Kekeba threshold here, and also a bit above. Okay, so in the fitting procedure, we had 12 parameters. So we had the parameters A00, the 2 chiral 0, and some mass of resonances. And the Bootstrap procedure basically chooses its best position by using this particle swarm. And here is the Bootstrap fit that we did. So the error bar is given by using all the different amplitude obtained in this particle swarm optimization and select the one with the lowest, with the one with a reasonable chi-square, and doing a weighted average. And so that gives the error. And for example, the first scattering length, you can see it's really close to the one that you can find in the literature. And similarly for the mass of the different resonance, that there really matches the one you see in literature. And here I recall that the width of the particle, decay width, is given by the imaging. Regarding the two chiral zeros, so because we have a phonetic function, we can actually plot the amplitude also below threshold. And so here we compared with KPT. And so the amplitude obtained from Bootstrap is the one in black in each of these channels. And in the dotted line, you have in green a tree level, which is a straight line in all channel. And you have 1 and 2 loops from KPT. And really you can see that the Bootstrap one, it seems to be the convergent curve for the loop computation, perturbation computation of KPT. So really here already we use this information. And I want to remind you that we did not impose the position of this chiral 0. We did just impose their presence, and the Bootstrap chose the best one. And so it's really, I think, beautiful. Okay. And now we can go further because we only fitted, we only fitted those data, but now we have more data that we can compare and see if the amplitude we got is reasonable. The first check is to go in the D2 phase shift. So this, we didn't fit those data. So now we just look at amplitude in this channel and we compare with experimental data, given as this orange and green error bars. And again, we see that this amplitude beautifully passed through the data. And also, again, in the inelasticity, only some amplitude we got had some dip in the inelasticity. And it's really close to some Fenner-Trout parameterization of this intensity that we found in the chart. So the next step is that now that we have an amplitude, we can do some spectroscopy. So the first thing we can do is go to the S0 wave. So to look at resonance, you simply look at the complex plane. So you look in one channel, so in the spin 0, isopin 0 channel, look in the complex plane. And when you see a 0 of the absolute value of the partial amplitude, it's indicate the presence of a resonance. So these two here, they're a parameter of the fit, but the position were chosen by the particle swarm procedure by minimizing the chi-square. But the sigma here is dynamically generated. So it's a particle that has to be there in order to fit the data. And so here you can go into PDG and look at all the determination from, I think, 2001. And it's all these violet ellipses here. And the average is this big violet one. And the Bootstrap prediction is this little black dot here. And how do we get an ellipse? So we have multiple amplitude, which has low chi-square, and we do a weighted average of the mass and width respectively. And we get this ellipse. The red dot are all the Bootstrap amplitude we took to make this average. Very good. So that was in one channel. So now we can go in the next channel, so in the P channel. So it's either spin one channel. So the row was again a parameter of the fit, but the position was chosen by the procedure. It's here. And we have a daughter resonance which appears and is generated dynamically, is the rho prime. And it has a mass close to the one from that experimentally observed. Okay. And okay, doing that, we can now look into more wave, and we found a surprise. So now if we go to the isopin 2 channel in the S wave, so in this wave, people do not expect to see anything, and no particle have been observed so far. But if you look at the Bootstrap amplitude, so we fitted those data, and if you look at the Bootstrap results, you see a signal of resonance. And now if you actually look in the complex plane to do a plot similar to what I showed before, you see that you have a particles with a mass and width. So its mass is roughly 2 GeV in a physical unit with a width of roughly 600 MeV. And this particles is a genuine tetraquark. And now we go into the PDG, and you don't find any such state. And so this is actually a Bootstrap prediction. And we may hope that it's maybe observed in the future, for example, in the LHCb experiment. And so here it's a similar plot of the phase shift, but now we plot the real part of the partial amplitude imagery part. And the imagery part here is actually the signal that we would see in an explicit experiment. So if you want to look at this particle in an experiment, you should try to fit this signal. Okay. So now it's quite interesting that using this procedure, using the Bootstrap, we get the prediction of a new particles in order to fit the data. So it does not stop here. So now we can look at different regime in your amplitude. So one of the regime of interest may be the UV. So now we can look at the cross section. So we look at the pi plus pi minus and pi minus cross section in the amplitude, and here we compare. So we do not fit this data, but we compare with this data. And for example, here you see that the feature that you observe, they really match closely the data. And this bump here is really the presence of this different resonance that we have in the Bootstrap. And you see that they match beautifully the data in this channel 2. The two color here, they refer to two sides of the ansatz, to see how it will change. And also we can see that these data, they're quite old, first of all. And some of them are really have different shapes. So for example, those here from 6 to 7, they're really different. So some care has to be taken, maybe if one wants to actually fit those data. Okay, so let me summarize the spectroscopy that we did. So in the beginning of this talk, I presented this plot with the gray box being the particle actually observed so far that you can find in the PDG. So you have the sigma, the F2, etc. Using the red box, these are the particles that we found in the spectrum of our amplitude that we fit it using the Bootstrap. So you can see that the sigma has roughly the same width that you can have in literature, but the mass more on the lower part of it, but the error bar is much smaller. And similarly for the 2F0. And the rho is roughly the same because the data are so precise that roughly the same. For the row prime and the row tree, we still have some systematical error that we think that once they are fixed, they will the match will be much better. And here, this is the new tetrachord web there, and of course you don't have any gray box because there is no such state in the PDG, at least as of today. And so, with that, I think I would like to summarize this Bootstrap fit procedure. So what is the input? The input is experimental data in 3 different channels up to some energies. So this experimental data. I didn't explain, but we also use some explicit university models for the same waves, because it's interestingly important to solution of such particles, and it's hard to obtain elasticity as a result of the Bootstrap, at least when you do just 2-to-2 scattering without doing a mixed channel. And so here we use some explicit models that are coming from measurement to impose some elasticity. Then we impose the presence of chiral 0 and the presence of some resonances. Then we go through this Bootstrap fit machine, and as the output, we fit it the phase shift, the chiral 0, and the resonance position. We also get scattering length and effective range. So I didn't show you the table, but you also get scattering length of the channels and effective range. We also can compare with KPT in the real strip. Then we match the D2 phase shift and elasticity, which is compatible with experiment. And we dynamically generate a few resonances, the sigma, the rho, the rho3, plus a third quark, which are at the correct position. And finally, we can compare with the cross section. And again, here the match is really interesting. So with that, it brings me to my discussion and future direction. So in this work, we had a novel approach to fit the data using Bootstrap technique. So I can remind you that in the last few years, we developed this H-matrix Bootstrap, and we mainly studied some different models, but now we try to use that to fit data from the real world. And we use the power that this function that you get out of it satisfy all the Bootstrap constraints, so analyticity, crossing, unitarity. So really the theoretical error on this the theory is really under well control here. We reproduce all the known spectrum, and we also predict new particles. And of course, what we like to know is can we observe it? Is this particle real, or is it some produce of our procedure which cause this particle to be there, but is not there in the real world? So this is something really interesting to know if we can observe it, and this is something we're trying to talk with people from LHCb. Then this procedure has some systematics as maybe any procedure, and so there is some improvement that can be done, and we are working on them. And with that, we can have more precise determination of these different resonance. And for example, has a better rho and better rho prime and rho prime prime and rho3, sorry, compared to experimental observation. And then we didn't perform that here, but we can also actually continue the sampling in spin. And for example, look at the explicit trajectories in the QCD spectrum. And for example, check that it's believed not to be the case, but check if the sigma is part of a trajectory. So it's because it's in the spin 0, so it expects not to be part of any trajectory, but we can actually continue the trajectory in spin and see if the sigma is part of it. And we can also measure form factor using form factor Bootstrap. And here it can be interesting because it may have some relevance for G-2, the hadron computation to G-2. And maybe the last one, which as people coming from Bootstrap, we may wonder, is can we obtain rigorous bound? So here we did a fitting procedure, and we predicted the position of resonance using this procedure, but we did not put bounds on position of this resonance. And so one may wonder, can you do the opposite? Can you say, where can a resonance not be? And so there is a paper some years ago by Bharat Gabai and Shi Yin, where they did that in 2D, where by knowing some data and relaxes, they managed to put bound on information in the complex plane. And it may be possible to do that here as well. And this could be interesting in order to maybe it triggers bound on position of some resonance. So with that, I thank you for your attention, and I'm happy to discuss more and answer any question you may have.
Thank you very much, Kelian. So now, are there any questions?
So about this new particle, did you give it a name or?
Did we give it a name?
Yeah.
No, it's a tetraquark. We did not have a name. No.
So yeah, do you expect that it can be observed in the near future, or you think you need?
It could be. It could be observed, and we suspect that no one observed it or so far. One of the reasons, maybe multiple reasons, but one of the reasons is that no one expects to have something in this channel, so no one maybe looked.
Yeah,
that's maybe one of the reasons. Then you see it's at 2 GeV, so it's relatively high energy, and there maybe you have more noise, maybe it's more difficult. But still, in an LHCb experiment in beta decay, you can observe in a B decay, you can observe this. You have enough energy to observe these particles, and so we hope that there it can be done. And one of the difficulty also maybe is that if you look at the profile, so often when you have a resonance, you have a bump in the imaging part. But in this case, you have a dip in the imaging part. It's not a bump. Usually it's like a bump, which if you have an experiment, if you see a bump, it's really clear that you have something. But here we have a dip, so the signal is less clear if you do an experiment. And so that may be also one of the reasons was not detected yet. But we are now in contact with people from LHCb, and they will try to add that to the fitting procedure. Yeah. So we have some hope.
Yeah.
But it may be a region when you have also a lot of noise, so it's a bit, I don't know. I don't know what to expect here.
Can you go a few slides before that one?
Yeah.
Yeah, that one.
Here?
No, after that. Yeah, okay, that one. About the last graph. So I guess your fit, well, it fits more or less the experimental data, right? For most of the points.
Sorry, I didn't get your question.
So there in the last graph, you're showing your fit. Or
yes.
With experimental data.
Yes.
Okay, so for most of the points in the experimental data, your fit seems to be pretty accurate within the error bars. But well, there are a couple of points that it seems to be missing. Do you think it's related with improving the systematics that we mentioned?
Yeah, it has the systematics, but also this data you sometimes need to be careful about the error bar. I don't exactly know, but maybe to the end here we have some systematic error and should be more flatter. Maybe I agree, and this could be improved with systematics. But here, for example, look at around 40 here. This is two different determination that they really separate to each other. So you need to be careful with data. But again, here we did not fit those data. It just we compare with our prediction. Yeah. But maybe it's related to the systematics dispersion. Yeah. Maybe here we should be for flat. I agree.
Okay, thanks.
Yeah, I had a related question. So this seems to happen at large S in all your plots. If you go to the very first fits that you showed.
What happened large S?
Before this?
These changes.
Yeah, yeah. So a few slides before, when you do the first fits.
Yes.
Yeah, here. So this kind of feature, this is always there for, a large S, right?
Yeah, you mean here, for example?
So does that have anything to do with your systematics or the data or something physical?
Yeah.
Going
So here, for example, here at this point there is this kickback threshold. So there's a new threshold opening up, and we did not put this threshold into the ansatz. And for example, we believe that one of the source of the systematic is because at this point we should put this kickback threshold into the ansatz to improve systematics, which would make it easier to pass through this data. And because here we observed that it was really hard for the numerics to to converge in its region for the inelasticity. And so this is related to the systematic. There's a difference here. And how it behaves here, it's a bit less clear. It's maybe also systematic. And okay, above
the same value, right? It happens around 40 or something.
Wait, what?
It happens around the value of 40 or 45 or something that this deviation starts to happen. So
Which deviation?
This deviation with the data that you're talking about, there's not a threshold that you need to add.
No, here there is a typical threshold of 55, I think. And so here you have a deviation that you expect to go higher. And but I wouldn't say it around 40. You have many things happening around 40, so you need to be careful. Yeah.
Okay, thanks.
Maybe I didn't get your question. Why 40?
No, I think you answered it. Thanks.
Yeah, here also you see that from 40 it's a bit more scattered because it's a bit more difficult to have good data from experiment. And here, this point here was really important, this lattice point, because you don't have much point between threshold and 30 here. So this lattice point was really important and also influenced the position of the mass of the sigma. Yeah.
Okay. Any more questions here or online? Okay, so if not, then and we can end.
Yeah, very nice talk.
Yeah, it's very exciting stuff.
Thank you. Yeah, it's an exciting project. Yeah. Are you working on similar